we have some excellent set of speakers for you guys. And I think you already met a few of them. Today we have a very special one, who happens to be a friend of mine. So Professor Woody Hoburg here is actually an MIT graduate with undergraduate. And after he got his undergraduate degree from MIT's Aeroastro department, the aeronautics department, he went off to Berkeley to do his PhD there with a professor who actually works on AI. But then he was in this lab and he learned about what we call optimization, mathematical programming, and he applied some of those techniques to aircraft design optimization. Aircraft design optimization is so hard that people build these aircraft designs and they put them into a computer and you have to wait for hours, if not days, to get a design that you don't even know if it's optimal. But his doctoral thesis kind of came up with some methods so that for certain kinds of airplanes, you can actually find the optimal solution in the snap of a second. So I think he's going to talk about some of those applied to building an aircraft that look like this, and it can stay aloft in the air for like a week.
5 days.
5 days, almost a week. And it's another pleasure to say that Woody actually is one of the astronaut candidates that were selected just this year. Among, I think, 18,000 applications, just 12 were selected. Actually, 3 came from MIT, and Woody was one of them. So he's headed. So as you know, NASA selects astronauts once every 3-4 years, something like that.
Yeah.
Class of, like every class will have 10 to 20 people. So Woody happens to be among them. I think he's reporting to the office very soon, and he's giving this talk to you guys. Please welcome Woody.
Well, thank you guys. I just found out a couple months ago, actually, that I was going to be going off to Houston for this training, and one of the hardest parts by far is leaving MIT. I've been on the faculty here for 3 years, getting to interact with amazing researchers and amazing students, and leaving is really hard. But I'm super excited. I thought today, for the agenda, maybe we could spend a few minutes, since it is on my mind, and as Surtesh mentioned, I'm going off to NASA. I thought we could talk for a couple minutes about astronaut training, and then I'll tell you about this airplane that can fly for 5 days that we've been developing here at MIT, actually as a BeaverWorks project. Okay, sound good? So this was 1 month ago. This is the latest class, the NASA 2017 NASA astronaut class. 18,000 people applied, and for some weird reason, they picked these 12. So amazing group of people, and incredibly diverse background and group of experiences. So like just going through here, Frank on the left is an Army Special Forces doctor. Zena is a microbiology researcher. Matthew there is a Navy test pilot. Jasmine is a Marine Corps helicopter pilot. I think I'm the token professor in the group. Johnny is a Navy SEAL and now emergency medicine doctor. Rob is a SpaceX engineer and used to work on fishing boats in Alaska. Raja is a Air Force test pilot. Zena's a nuclear warfare officer. She works in nuclear submarines. Farmer is a NASA research pilot. Laurel is a Woods Hole engineer, and Jessica is a JPL geologist working on Mars Science Lab. So incredibly crazy group of people. Behind us there is the T-38. I'll be flying in that later this fall. That's the aircraft that NASA uses to do spaceflight readiness training. And we do a bunch of training. We learn Russian language, and we'll go off do some wilderness survival and water survival training. That's Anne McLean and Josh Casada from the last class that was selected doing their wilderness survival training a few years ago. One of the things a lot of us are really excited about is going in NASA's Neutral Buoyancy Lab. This is down in Houston. It's basically a big swimming pool, and inside that swimming pool, it's about 40 feet deep, and there's a full-scale International Space Station underwater. And what this is used for is training for EVAs, or spacewalking. So this is Jessica Meir getting dunked into the tank. She weighs about 300 pounds there. She's got a full spacesuit on. She's ready to go do some EVA training. And the cool thing about this is you get to be neutrally buoyant. So you're just floating in the pool. You're not going up or down. And it's just like, about as close to spacewalking as you can get on Earth. There's a whole team of divers in there that helps with this. So every astronaut in the pool has 4 or 5 divers assigned at any given time, taking film, helping you to remain neutrally buoyant, adding weights to you to make sure that your buoyancy is perfect. So there's a huge, one of the amazing things about this is how many people support all the training and everything going on. All right, so I teach dynamics here at MIT, and I have to talk a little bit about all the cool dynamic stuff associated with being in orbit. So why are astronauts weightless in orbit?
Because they are actually under a constant acceleration and just not being, there's just no normal.
All right, good answer. So I asked that question to so many people, and it's so common to hear, oh, there's no gravity in space. That's like a really common answer. So let's talk about that for a second. The International Space Station is in low Earth orbit, right? Where is low Earth orbit? How low is it? Really low. Yeah, so low Earth orbit is 400 kilometers, which is about 1/32nd of Earth's diameter. So low Earth orbit is like there. It's really, really close to Earth. There's a lot of gravity in low Earth orbit. And you're just skimming along the surface, right? In fact, here's g. Little g is 9.8 meters per second squared. Here's a plot of g as you increase orbit altitude away from Earth. And the International Space Station is sitting right here at, by the way, why are these so blurry? Is there anything we can do with that? The International Space Station is right here at 400 kilometers. G is about 8.7 instead of 9.8. So it's less, but it's not much less. You're still getting pulled on pretty hard. And what's going on is, what's your name? Matthew. What's exactly what Matthew said. So the force of gravity is GMM over r squared. R is the radius of Earth plus the orbit height. And that force goes into an acceleration. And in circular motion, that acceleration is mass times, that force goes into a mass times acceleration, and that acceleration is v squared over r. So you notice it actually turns out that the higher you go, the slower you need to go. But the key thing here is that if you have the right velocity, then you'll be in a perfectly circular orbit. The force of gravity will balance out the acceleration needed to stay in that orbit. And it turns out at 400 kilometers, where the space station is, the velocity needed is about 7.6 kilometers per second. That's really fast. It's like 17,500 miles an hour. It's really, really, really fast. So if you look at a launch, this is one of my favorite pictures. This thing looks like it's crashing back into Earth, right? That's not what's going on. It's an illusion. That thing, this is a real launch. This is going up, and most of what's happening in a launch is not that you're going up, it's that you're going sideways. You're getting into orbit and gaining that 17,500 miles an hour. So all of that trajectory you see there is actually just downrange distance. That spacecraft is going faster and faster downrange to get the speed it needs to stay in orbit. All right, so that's just a quick, cool overview of some space stuff. I'm super excited. I'm not a real astronaut yet. I know nothing about being an astronaut. Everything I can show you is pictures from people that have gone through the process before me. I'll report for duty August 21st in Houston, and they'll start training us up, and I will learn a lot of stuff, and it should be an absolute blast. So what I'd like to do now is we can talk, I'll answer questions and stuff at the end, but what I want to do is actually tell you about what I've been really passionate about for the past year or so, which is a project I'm working here at MIT. I'm working on this with a bunch of undergraduate and graduate students and a couple colleagues. And the goal here is making an airplane that can fly for 5 days. So I want to tell you a little bit about this project for the rest of my talk. Okay? So this is actually a Beaverworks project. Beaverworks does a lot of things, and one of the things they do is set up capstone design projects for our students here at MIT. So our seniors, I teach in the Aeronautics and Astronautics department with Surtash, and our students here, when they get to be seniors, take senior design capstone classes where they kind of wrap up everything they've learned into a design project. And it's kind of not great if your professor just makes up a random project that they think is interesting. It's better if you work on something real. And so that's what's really cool here. We work with Lincoln Labs, and Lincoln Labs has real customers. And we work with Lincoln Labs to come up with real design projects that matter. And the students have real customers, in this case Lincoln Labs and ultimately the Air Force, for a project that actually has some application out in the wild. And so the idea for this year's project, actually the past few instances that I've taught this class, is to provide persistent aerial coverage. The idea is that in a natural disaster or some other emergency, Lincoln Labs is actually developing some really cool communication payloads that would be really useful to be able to hold over that emergency zone, for example, to provide communication relay if communication's knocked out. So to let people talk back and forth on a radio, or to send videos back and forth, that sort of thing. And so we want an airplane that would allow us to provide that capability over some area. It turns out providing persistent aerial coverage is super expensive. So Global Hawk is an aircraft that's operational today. It's in the Air Force inventory. You can, the Air Force can order Global Hawks to go out and do useful things. But providing 24/7 coverage of a, let's say, 300-kilometer diameter area would need about 5 airplanes, because you have airplanes transiting in, airplanes transiting out, some down for maintenance. So there's a lot of airplanes needed, and they each cost $131 million. And flying them is expensive too. It costs $32,000 an hour to have a Global Hawk in the air flying. Okay? So Lincoln's developing these really small payloads that can do amazing things. Like they can provide amazing communication relay capability, and the payload weighs 10 pounds. It's like 2 bags of sugar. It's a really small thing. It's not particularly expensive payload, and it seems way crazy that we'd have to spend this much money to fly that payload around. Lincoln has actually been prototyping these things on weather balloons. So put the payload on a weather balloon, launch it. You can get some really great operational experience with flying it, getting up to really high altitude. But there's problems with weather balloons. They drift. You can't bring them back to the same site you launched them from. If you care about the payload and either getting it back or having, not letting somebody else get their hands on it, then it's not great with a weather balloon. You don't really have control over it. So the idea was maybe we can do this with a cheap, fairly inexpensive airplane that would hold this payload in the air for a long time. So here's the sort of generic engineering problem. How do you hold a 10-pound payload up in the air for a really long time? So this is too vague to actually solve as an engineering problem. It's kind of the actual goal we have, but it's a little too vague. So what we break this down into is engineering requirements. We specify in a little more detail what we actually want to do. And you can see when we actually started this project, we didn't know how we would accomplish it. So you may have read ahead a little and know how we solved this problem. But when we started out, we actually thought that one of the likely solution options would be a solar-powered airplane. So we thought we would fly powered by the sun, and this way we could fly for days on end. And you can actually see that reflected in the requirements that we wrote down. So there's requirements about the payload, like its size and its power consumption. The really key requirement is staying on station for 5 days. And there's these threshold requirements and objective requirements. So threshold means it's good enough. That's check, you met the requirement. Objective is, well, if we could really have anything we wanted, if all of these were possible, this is what we'd really want. So you can see we were thinking with a solar plane we could maybe stay for weeks on station. But we need at least 5 days. By the way, no unmanned airplane, well, sorry, that's not true. Yeah, 5 days would be, it turns out 5 days would be a world record for the class of airplane that we ended up designing. So there's other things about flying into station, and then the station keeping requirement, I'm really sorry it's so blurry. It's not blurry on my computer. What's that? I don't know, if you tell me if it'll. Hey, nice work. Technology. All right. So hopefully your eyes will be okay now. Yeah, so the station keeping requirement, I drew that picture before where the airplane's covering a cone. It turns out for these comm payloads, you need to be able to see it up above the horizon at some angle, in this case 5 degrees. What this really translates into is an altitude requirement. So threshold altitude is 15,000 feet. If you're 15,000 feet up, you can see a big enough area. That's the requirement. And you can see we had a latitude requirement. The latitude requirement was, again, anticipating a solar solution. We thought, we know that it's not going to work at the North Pole in the winter. There's no sun there in the winter. So we know we're going to have some bound on latitude. And so we wrote down a threshold of plus minus 45 degrees latitude. So we need to be at least able to fly between those bands. And then availability really refers to winds. So this means we knew that winds could be really high some days, and it might be not possible to hold on station with such high winds blowing us. And so we wrote down a number where we said in 94% of global winds, expected winds globally, we should be able to stay on station for 5 days. Okay, so these were the engineering requirements. And we used some sizing methods, Surtash mentioned them earlier, that were developed here at MIT to size the airplane. It turns out sizing an airplane, or figuring out how big it should be, like if I ask you, I want to carry 10 pounds for 5 days, how big should that airplane be? It's kind of a catch-22, it turns out. Like, you'd say, well, the wing needs to be big enough to pick up the airplane. But then how big is the airplane? Well, it needs to carry enough fuel to fly for 5 days. Well, how much fuel does it need? Well, it kind of depends how big the engine is, and the engine needs to be big enough to push the airplane that's big enough to carry all the fuel. It's kind of like catch-22. And there's a lot of considerations that come in. Like, there's how you're going to operate it. There's those winds I talked about in the environment. There's aerodynamic models. It turned out we had to do some pretty detailed propulsion modeling and figure out how big the structures need to be to carry all the loads. So there's a lot of engineering that goes into this. We considered a lot of stuff. And we actually considered a few different options to solve this problem. So we actually considered 3 things, and I'm showing 2 of them here. We considered solar electric power, meaning you would fly all day on solar panels, and you would also charge batteries. And then during the night, the batteries would fly the airplane. And then in the morning, the cycle would repeat. You would fly on solar power and charge batteries all day, and then at night, repeat again. So that was configuration number 1 that we considered. And we had a bunch of models that modeled the solar flux at different latitudes and wind speeds at different latitudes, and modeled current solar cell capabilities and the efficiency of batteries and all this stuff. We considered a gas-powered architecture, and that means you take off with a gas-powered engine, you have enough fuel, and you fly for 5 days until you run out of fuel. And the third one we considered was lighter than air, like a blimp. It turns out lighter than air we threw away really fast. It turns out at that altitude with the winds, the power needed just to, it's great, you have a blimp so you don't weigh anything, you stay afloat, but you have to charge into the winds really fast. And you're this big blimp with a lot of drag. And it turns out the power needed to do that is just really, really bad. So that option wasn't so great, but we compared the solar and gas options in a lot of detail. And we used these methods that I mentioned to write this whole thing down, all these constraints on the design, as a huge, giant bag of mathematical models and constraints that have to be satisfied. And if you're interested in math, one of the cool things, which is actually one of the things my research group does here, is how you optimize simultaneously all these constraints that need to be met on the design. So we have some cool techniques that allow this to happen in seconds, actually. So we have hundreds and hundreds of design variables. in some cases thousands of constraints, and we can find the optimal airplane in under a second. It's very fast. So with that capability, we did some early studies, and this was actually just like 3 weeks in to this development effort, and we compared solar and gas. So what you're seeing here is, on the left, we're plotting things against latitude. How far from the equator are you? And in blue, you see solar, and in red, you see gas, and the y-axis is max takeoff weight. So it's how big is the airplane? How heavy is it? How much does it weigh? And the different bands, the confidence bands there are different wind speeds. So we wanted to understand how sensitive this is to wind. And each point on this graph is a different optimized airplane. So it's got hundreds of design parameters that have been carefully chosen that allow it to fly at least such and such a latitude in such and such wind speeds. So we optimize the airplane for a certain latitude, like let's say plus or minus 25, and we find out how much does that weigh. And then we re-optimize a different airplane for 35 degrees, and we find out how much does that weigh. And what we noticed very quickly was that the solar option, the blue one, blows up with latitude. So the further away from the equator you get, the airplane just gets heavier and heavier and heavier, and it actually gets to a point where it just goes off to infinity. It just gets impossible. At least with the current assumptions about battery energy density and solar cell efficiency and all the assumptions that we put into the model. If we believed all that, the solar concept blows up, and you notice our requirement was 45 degrees latitude, which is over here. So things were not looking good for the solar option. I can give you a little bit of intuition for why that is. As you go away from the equator, 3 bad things happen if you're trying to make a solar airplane. One is you have less solar flux. So during the day, less solar energy lands on you. If you have solar cells on your roof in Boston, you collect less energy every day than solar cells on your roof in Florida, period, just because of latitude. The second thing that kills you is you have to store the energy to fly all night in batteries. And it turns out at higher latitudes, the solar flux comes in over a shorter period of time. The night is longer. So the day is shorter, the night is longer. Even for the same amount of solar flux, it's coming to you in a spikier way. And then you have to store it all night long. And so this causes the size of the batteries to get bigger and bigger at higher latitudes. You just need more battery because the night is longer. That's 2 things. The third thing that kills you, it's almost ironic. It turns out if you model wind speeds around the world, as you move up away from the equator, up to about 45 degrees latitude, wind speeds get higher and higher away from the equator. So the further you are from the equator, the more you have to fight the wind. It actually peaks around 45 degrees and then gets better as you go up toward the pole. But by that point, by the time it starts getting better on winds, it's a lost cause in terms of the solar flux available. So these things just kill the solar option. And it turns out the gas option is pretty insensitive to latitude. It gets a little bigger because of the wind effect. But that's it. So this increase in size as you go up in latitude is just those winds getting a little faster. So we took this information and we had a lot of data backing it up, and we made the decision very early on to go with the gas option, which was a little bit counterintuitive for many of the people working on the project, but we were pretty confident in it. You can actually see how the max takeoff weight would scale with the number of days we wanted to fly for. So you can see that flying for many days, like over a week, starts to get pretty big. You're carrying a lot of fuel, and that fuel is carrying more fuel. There's an exponential blow up of the amount of fuel you need. But down here around 5 days where we wanted to be, things looked pretty good. And we actually put in 1 extra day of margin in the design. We went for a 6-day endurance airplane, just so that we'd have a little bit of safety factor. All right, so we decided to move forward with the gas. And this is the concept that we came up with. It's a pretty simple, standard airplane configuration as airplane designs go. It is actually launched from a car. That avoids the need for landing gear that can get us off a runway. We can just launch it off of any vehicle. It climbs up to 2,000 feet. It climbs up to 15,000 feet. It cruises into the station or the location that we want to cover, and it stays there for 5 days loitering. It has an autopilot on board. It autonomously loiters for 5 days over the station. And then it flies back and descends. And we have an RC pilot for takeoff and landing. And then we use the autopilot for the rest of the mission. To be clear, we haven't flown for 5 days yet. We have had our first flight. So this is a development project where we're trying to, our ultimate goal is to fly this airplane for 5 days. And I'm going to tell you today about some of the work we've been doing on developing this thing, some of the challenges we've encountered along the way, where we're at in the process. We just had our first flight May 4th. So it was very recent that we even flew for the first time. And we're quickly moving through more and more testing of the airplane. This is the vehicle. This is what came out of that sizing. So this is the optimal airplane, at least according to all of our assumptions, for flying the mission we want to fly. Taking into account all the assumptions that we have. So it weighs 50 pounds empty. Empty weight means no payload and no fuel. So it's just the airframe and the engine and all the stuff needed to fly the airplane. That's 50 pounds. The design takeoff weight is 150 pounds. So that extra 100 pounds breaks down into 10 pounds of payload and 90 pounds of fuel. It's a lot of fuel. We're flying for 5 days. But if you think about it, 90 pounds of fuel is 15 gallons, which is about what goes in a standard car. So with what you put in your car in one fill-up, we can fly this thing for 5 days straight, which is like, if you think back to where you were last Sunday, we would have taken off on Sunday and we'd be just landing now. It's a pretty long time. We can carry different payloads. We actually have a minimum payload. The minimum 5-pound payload is for weight and balance reasons. So we need the center of gravity to be in a stable point. So we need at least 5 pounds up in the nose. We provide 100 watts of power to the payload. It loiters at 15,000 feet at 48 knots, which is that 94% wind speed. And it has a 5.4 horsepower engine. At least it provides 5.4 horsepower at sea level, and then it provides a little less power as we climb up in altitude. This is the overall configuration. So in the front is this payload bay. That's what houses the cool payload that Lincoln's making for us. Behind that is our avionics bay, where we store all of the electronics that do the autonomy, that control our servos, that control the engine, control temperature, that interface with the payload, allow us to do RC control, power management. There's a bunch of stuff in there. Behind that, the cylinder is a giant fuel tank. That's 90 pounds of fuel. Behind that is the engine mount and aft landing gear. It's a pusher configuration, so the engine actually pushes up through the sky instead of pulling. This pylon functions as a cooling duct and air intake for the engine. And then there's a 24-foot wing on top, which breaks into 3 8-foot sections for transport. We have these wing joiners that allow that to happen. And then in the back is this carbon fiber tail boom with a horizontal and vertical stabilizer in the back. You notice, so the whole thing's made out of carbon fiber, which is really lightweight and stiff material. You'll notice the payload bay and the tail are yellow, and that represents Kevlar. So those are made out of Kevlar instead of carbon fiber. The reason for that, does anybody know actually? Yeah? Yeah, it's RF transparent. So it turns out in the payload, we have some antennas up in the payload, and we have a payload antenna mounted on the tail. And it turns out carbon fiber is conductive. It's like metal. And radio waves can't propagate through carbon fiber very well. They can get through Kevlar just fine. And so anything that has antennas mounted on it or near it, we've elected to go with Kevlar instead of carbon. All right. Let me show you a little bit of what we did to make this thing. We spent 2 semesters designing, just figuring out what everything would look like, doing the design of what would be inside the wing, and then 1 semester actually building it. So you see inside the wing has a carbon fiber skin on it, and inside there is a foam core and then some spars, and the spars take the bending loads on the wing. So you want, just like an I-beam, you want a lot of structure spread out as far as you can get from the center line of the wing. And that's these two spar caps. You can see them best here. This black thing on top, and there's another one on the bottom. Those are like the beams of an I-beam, and that takes all the bending loads in the wing. There are these wing joiners, which have to take the loads between the tips and the center section. And we make this whole thing here at MIT. So this is this mold here. We actually manufacture using a CNC router here in one of our labs. And then it's a two-step layup. So the first step, we bond the spar to the foam core in the mold. And we put in some little hard points for attaching the wing to the rest of the vehicle. And then in the second step, we put the skin over top of the foam core, and we get out our wing center section. And then we do the same thing for the tips. It's a lot of fun. Here's Mike and Rob down in lab. These guys actually, so Mike was an undergrad at MIT. He was in the senior design capstone. He then became a graduate student, actually working in my lab, and continued helping with this project. He's actually away at a summer internship right now, working on some other airplane design stuff, but he'll be back in the fall actually leading our ongoing effort on this airplane. So, and then Rob is also coming back for his senior year next year. He made a bunch of parts on this airplane, and these are just two of the students that spent a bunch of time working on this. Here's a whole crew downstairs doing a big wing layup. It takes a lot of people. You need people to cut things out, mix epoxy, roll epoxy, get molds ready, wax the mold, carry stuff around. It's a pretty involved process. Here's the fuselage. So that was just the wing. The fuselage, as I mentioned, has this forward avionics bay in front of which is the payload, and then behind that is all this fuel. Two 7.5-gallon fuel tanks just inside this cylindrical fuselage. It's got a rear bulkhead that mounts the engine. This fairing makes the engine low drag and provides a cooling pathway for cooling air for the engine. And then this pylon gets the wing up above the fuselage. It removes some interference drag, and it gives us that air inlet. Here's the manufactured fuselage. We again made it in-house. A lot of manufacturing that goes into this. Let me show you a quick video, if this works. So here's a time lapse of, this is just one tiny part of the, oh, it is showing. Okay, this is one side of the pylon. So this is one little part of the airplane, and here's what it looks like making that part down in the lab. So we make these things in molds. We actually put this vacuum material on and pull vacuum on it, and then we add some extra pressure with weights. So you can imagine, this is one small part. I don't have a time lapse of the wing, but the wing is even crazier than this. All right. So we did some testing prior to flight. This is a really fast development process. So in a real big airplane, you would do a ton of testing before you ever fly. You would test every servo for a really long time to make sure it's not going to wear out. You would you would do a bunch of computational modeling and testing. You would do all this stuff to just make sure that you're actually ready for flight. Here we were being really aggressive. We were trying to fly and develop this whole vehicle really quickly. So we didn't have time to do as much testing before our first flight as you would normally do. But we did some critical tests. We did some testing of like critical elements that really matter, and one of those is the wing. So before we went out for our first flight, we simulated the loads, the bending loads that would be on the wing. And it turns out you can do the math to figure out the bending loads in a wing. In the real airplane, the loads are distributed because the lift on the wing is distributed from tip all the way into the root. So you have a distributed load pulling up on the wing, and then you have a point load of the fuselage pulling down in the middle. And you can do the math and figure out what the bending loads are. It turns out that loading a wing in this way, where you have a point load pushing down in the middle, and then just 2 point loads pulling up on the tips instead of that distributed load, it turns out that this is actually worse for the wing. This puts more load on a lot of different sections of the wing than we would actually see in flight. So this is like a conservative test. It was successful. We were able to, the wing held together and didn't deflect more than we expected. You can also see here a wing section that we intended to break and did break. So here we brought the wing section all the way to failure. We put it in a press and pressed it until it broke. And we verified that it broke at the point we thought it would break on based on our analysis. This is the tail of the airplane. Again, you see it's made of Kevlar. There's some servos back here. There's actually redundant elevators. One of the concerns is what if one of your servos or control linkages breaks or fails in flight? You don't want to be completely uncontrolled in pitch. So we actually split the elevator into two sections with two independent servos controlling them. And we'd like to have the full control authority of both servos, but if one of them fails, we still have enough to get the vehicle back on the ground safely. So it's just a little bit of redundancy there. I mentioned the vehicle-assisted takeoff. The landing gear here is really minimalistic. We want to fly for 5 days, so we don't want landing gear to add a lot of drag or weight. We want as little as we can get away with. And I think we've achieved that. We have a rollerblade wheel in the back. It actually, when the landing load hits this wheel, it compresses this little stopper, which absorbs some of the vertical energy, the kinetic energy of landing. And we land rear wheel first, and then the airplane ends up touching its nose down onto this front landing skid, which is just a piece of metal that scrapes along the ground. So this is just enough to bring the airplane in for a safe landing. We've done that several times. And one of the interesting things here is if you've been paying a lot of attention, you may have noticed that the prop diameter is larger than the fuselage. So it turns out, if you look at the airplane from the back, the lowest thing you see is propeller, which doesn't work so well for landing or takeoff. So the way we get around that is that the car has a launch rack that provides clearance for the propeller. The airplane actually leaves to the back of the car. It backs up as it takes off because the car is going so fast. And for landing, we actually intentionally kill the engine. So once we get on final, we're assured a good landing, our pilot has a button that kills the engine. We kill it. It preferentially stops roughly horizontally so we don't strike the prop, and we come in for a landing. So that's kind of, we had to grapple with a lot of issues, and early on we weren't sure what are we going to do about like the propeller, and do we need to have landing gear that makes enough room for the propeller? Well, that's going to add a lot of drag, and this is how we solved it, this simple scheme of just stopping the propeller. The launch rack mounts on any standard car. I volunteered my car. That's my little Mazda sedan that's been beaten up through all of our horrible, just lots and lots of students crawling on top of it, mounting things to the top of it. So we put this launch rack on it that holds the vehicle. In the front, we actually had a failure on our second flight. On our second flight, the airplane bounced out of the launch rack. We were taking off from a grass runway, and we hit a bump, and the airplane bounced out just below its stall speed. We were just barely too slow. So it was like mushy and not very well controllable, and we actually kind of had a hard landing / crash, which was fairly easy to repair, but that was definitely a failure of the system. We don't want to be releasing from the car early. And so we upgraded it, and we put in this solenoid-actuated release pin. And what this does is it's a pin with a couple balls on it that lock it into the airplane, and then there's a solenoid below that we can remotely actuate, and it just releases that pin. So we hold the airplane down until the car is going 1.5 times the stall speed of the airplane, and then the pilot commands release, 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 and somebody pushes that button, and the airplane takes off. So it's a really clean, predictable release now. I'm going to go fairly quickly through this so we can get to some videos. These are fuel tanks that hold all the fuel. We had to split the fuel tanks into two because as you climb up, you don't want to have the fuel in the front going away because it's on the top, and a bunch of fuel in the back, and have the CG of the airplane move back too far. So that's an issue that we solved by having two fuel tanks. We have a fuel delivery system that makes sure the fuel gets to the engine. We actually have 2 engine options that we're still carrying forward in our development. One of them costs about as much as a car. It's a $19,000 engine. Now what we get for that $19,000 is a fully integrated system. It has an alternator to provide electrical power. It has an electronic fuel injection system, which is pretty rare in this size engine, but they've got that all integrated in. So it's an off-the-shelf system. It's fairly low risk. The manufacturer has tested it a lot. We can just buy it. We can spend our $19,000 and we have an engine. Or we can buy a $600 engine, which is a lot cheaper, and attach in-house a $1,600 fuel injection system and a $1,500 alternator to provide electrical power, and try to integrate that entire system here at MIT. So we've actually been doing both. We see advantages to both of these. Our initial tests have used this cheap engine, actually. We're using the cheap engine because if we crash, it's not so big a deal. We don't crash a $19,000 engine. And we think if we can get this thing working with our own fuel injection system and alternator, it would allow the whole airplane system to be a lot cheaper, which would be pretty beneficial. We'd like it to be a cheap airplane. But we're carrying both of these forward as potential options. We had to do a lot of work to integrate our own alternator into the TP70. Here's some diehard students out in the cold in like February doing brake-specific fuel consumption testing, figuring out what the fuel burn on the engine is going to be. That is a scale. That is the fuel tank on the scale. This is our very simple contraption to simply measure how much fuel has been used over time. And we're just running this engine, finding out how much fuel it's going to burn. We did a fair amount of that testing. It's not easy to get fuel. We need fuel injection for 2 reasons. One is it's going to burn less fuel. A carburetor will typically burn more fuel than a properly tuned fuel injection system. And number 2, as we go up to altitude, the density goes down, and the mixture of air to fuel needs to change as you go up to altitude. So if any of you are pilots, you know you have to lean out the mixture as you go up to altitude. So we have the same problem here, and we think the easiest way to deal with that is with fuel injection as opposed to trying to tune the mixture on a carburetor. It turns out this testing is, we've had all sorts of, I'm going to just show you a random video I found, which is pretty standard like engine testing, where we had an issue where the fuel injection system was in some bad resonance and was surging. So that's just another day at the office with the engine not working very well, where we have to go in and debug and figure out, hey, why is it surging like that? Why isn't it running smoothly? So we've been able to figure all that out, but it's just kind of bumps along the way. The avionics system ultimately controls the airplane. So it moves all the servos on the airplane. We have 2 modes. One is a pilot controlling everything. It's RC, so we have a transmitter on the ground. The pilot's just flying the airplane. But then we can flip a switch and we go over to autonomous mode, where the autopilot on board uses its sensors to steer the vehicle and navigate around waypoints and so on. So we have a bunch of components and sensors on board the vehicle to allow us to do that, a bunch of servos. And up in the avionics bay, we have all of the electronics boards that allow this to happen. So do you guys use Raspberry Pi at all? In this, as part of, not as part of this, but OK. Some of you have used Raspberry Pi. So we have this expensive thing called the Micropilot, which is an off-the-shelf commercial UAV autopilot. And that really is like a good off-the-shelf system that can take in the sensor data and move the servos to fly the vehicle. What it doesn't allow us to do is kind of all the extra stuff we need to do. For example, we need to be able to turn on and off the payload. We need to be able to move a servo that controls the cooling flow on the engine. Move another servo that controls cooling flow to the payload bay. We need to be able to interface with our satellite communications link. So we do all that by programming our own code on the Raspberry Pi here. And there's a bunch of other components that come into this. We do have some redundant control surfaces. These are the ailerons that provide roll control, and then inboard of that are these flaperons. The flaperons give us some roll control, but also allow us to deflect flaps, which slow us down for a safe landing. So we can do glide slope control and slow down to the speed we need to be at for a safe, or at least for a gentle landing, I should say. Same thing in the tail, a couple redundant elevators, and then the rudder provides yaw control. Our testing strategy is pretty interesting. It turns out getting approval to go, you can't just take an airplane and fly it up to 15,000 feet. The FAA does not like that. So we have to be really careful about what we're allowed to do legally with testing. And ultimately, we want to take the airplane up to 15,000 feet and fly it. To do that, we have to do a bunch of stuff. We have to get an airworthiness certification. We're probably going to fly in restricted airspace so that we're separated from other vehicles. So we'll fly in a test range. So we're doing, and I actually literally walked here from a 2.5-hour telecon with the Air Force, where we've been kicking off our airworthiness process to get this vehicle legal to go fly in that restricted area. So we came up with a cool strategy. It turns out if you can go buy a drone and go fly the drone around yourself. You don't need FAA approval to do that. What you're operating under when you do that is called FAR Part 107, which allows you to fly unmanned aircraft that are under 55 pounds, under 400 feet, and under 100 miles an hour. And we actually made this airplane, as part of the initial sizing, we made sure that it would be lightweight enough that with no payload and very little fuel, we could fly it under 55 pounds. And that's what we're doing. So we just get it barely, it's like 54 pounds. We get it barely under. We fly it under 400 feet out at a little airport up north of Boston called Plum Island Airport. And we've been doing our initial flight tests where we work out some of the issues with the system under those rules, and we don't need approval to do that. And then in parallel, we're getting approval to go up to higher weights and so on. So you can see here some configuration differences. We have what we call the V0 configuration and the V1 configuration. And V0 is under 55 pounds. V1 is up to 160 pounds. V0 is low altitude. V1 can go up to high altitude. V0 has very little fuel. V1 has a lot of fuel. And then because of the weight limit, we're actually not able to carry some of the key components that we need for V1 on V0. So we don't have the engine cooling, we don't have the transponder, we don't have the alternator on board. But anyway, I thought I would show you, we've been doing a fair amount of V0 testing. We've actually gone out to Plum Island on 5 different days. We have 9 total flights so far. The airplane has launched 9 times. We've got a lot of experience with launch and recovery. We've demonstrated transferring back and forth between manual and autonomous mode. We've tuned the PID. PID stands for proportional integral derivative. That's a type of control law you can use. That's what the autopilot uses to actually control the vehicle. So we're tuning the gains of those controllers. We've demonstrated fully autonomous flight around in a figure-8 pattern. And I thought I would just show you, we actually got a pretty cool, one of our students edited together a pretty nice video from the first flight. So I thought I would just show you the very first flight of the vehicle. You'll see we were all very nervous. And I'll show you what that was like. And he set it to some epic music. Sorry, avionics ground station. Those are shoes, yes. He's calling out speeds for our pilot, so that our pilot knows he's away from stall. So we're lucky. We're lucky to have a very skilled RC pilot in the house. All right. Cool. So so those flights last a few minutes. We only carry 3 pounds of fuel. We're moving this summer and fall into flying at higher weights and for a longer time. We have a bunch of test objectives, and we're getting approval to go do those tests. And so far, everything's looking really good. The airplane has all of the performance numbers that we have so far from testing are right in line with what we expect. And we really think we have a vehicle that's capable of flying for 5 days. So obviously, there's a bunch of kinks that we need to work out, little engineering issues. Connectors popping loose and all sorts of minor things, but the fundamental concept seems like it's actually ready to go fly for 5 days. So we're pretty excited about that. Here's the team, very excited after the first flight. So let me stop there and take any questions you guys want to ask. Thanks for your attention. You want to manage? Okay.
Do you have any concerns about the gain for wind control changing as you go up higher and air density increases?
Yeah, great question. Absolutely. And the density is one effect as we go up. That matters. Actually, one thing that matters even more is the change in weight. So on the real mission, the airplane starts out at 150 pounds, and it finishes the mission weighing about 60 pounds. That's more than a factor 2 change in weight. What people typically do for this sort of issue is what's called gain scheduling. So you have a parameter that you know matters, for example, weight, maybe density as well, and you schedule gains to change as a function of that. So, yep. Yes, ma'am.
How fast do you have to get the car going to get up?
Great question. So we actually calculate that speed that we need for rotation really carefully. Our rule of thumb is we don't want the airplane to stall, and so it needs to be fast enough to not stall. And we actually want the airplane to move backward when it comes off the car. So we want it to be going fast enough that at the low throttle setting we're at, it'll actually have enough drag that it backs up off the car. And so what we've found is that a good speed is 1.5 times the stall speed. And so to finally answer your question, for these early tests where the airplane's lightweight, that speed is 50 miles an hour. When we go up to high weight, it's going to be faster. It's going to be like 65 miles an hour, maybe 70 miles an hour. Yes?
question about the data controller. And since it's kind of, there's no real mathematical or systematic way to test the gains.
Yeah.
How are you testing it now when you can't do actual like flights and real tests with the actual weight and stuff? Are you just doing simulations or are you?
Yeah, so we're tuning the gains with the lightweight version. And what we do is it's basically a two-step process. We can measure some parameters of the vehicle, weights and inertias and control surface sizes. And there's some rule of thumb, like equations and procedures you use to get a gain out of that. And so that's step one. And then with those gains, we go up and fly. And the micropilot has a procedure which allows you you do a bunch of different types of flying. There's something called Latitude arcade mode we go to. But basically, you fly the airplane with some varying control inputs. And there's a procedure that updates the gains to make them a little better. And so we just follow that procedure, and as we go to higher weights, we'll redo that procedure to get good gains for the higher weights. It turns out if you're a bit off in the gain, I mean, if you're way off, it's really bad. If you're just a bit off, it's either just a bit sluggish or a bit too snappy, and so it's not horrible. Let me take something from the other side. Yes, sir?
So what was the most difficult part about building the airplane?
I think it's hard to answer what was the most difficult question, but I think it was probably schedule. We were under a really tight schedule. And so, and we have such smart students. And like we had a great team, but it's really easy to get sidetracked onto something that's really cool, a problem that's fun to solve, but that ultimately we don't have time for. And so sometimes a quick and dirty fix ended up being what we needed. And that's really kind of tough sometimes to make that hard decision of, no, we're just going to do it this easy way, but we're going to keep on our schedule. I think that was, yeah. Yes, sir?
So what sensors did you use to estimate the state for your autonomous?
Yep, so that's a good example so a lot of our students would really love to go build an in-house like state estimator and an in-house autopilot. We bought one off the shelf. And that commercial autopilot has a few sensors that it uses to do state. So it has a pedostatic system, which has static pressure, so barometric altitude, and the pedo ram pressure, which is airspeed. It's got an onboard IMU, so it's got accelerations and attitude rates, and it's got a magnetometer. And it's got a GPS. So it's basically everything you need to get a really good state. Yeah?
So like in the case of a disaster happening, how many planes do you think would you have to go out and do a mission?
2 to 3. So 2 is enough to do the mission in the sense that when one runs out of fuel, you send the other up. And you've got plenty of time to transit in and replace one for the other. So you only need 2 from that point of view. But the reality is often you have like a plane down for maintenance. And for that reason, I would say 3. Yes, sir?
You had said that typically projects will go through Lincoln Labs and then to the Air Force. Do you think this is the type of project the Air Force will be using in 5-10 years?
We really we think this is a new capability, and that there's a lot of groups in the Air Force that seem interested. It's a very low budget project. So we are not doing, if the Air Force went out and wanted to procure a new UAV that does this mission, they would spend way more money and take way more time, and it would get bidded out to large contractors to do. We are doing something really cheaply, and so from where we are now, we'll need probably a company or possibly Lincoln, but we'll need some organization other than MIT campus to step in and take it from basically a prototype to an operational system. But I think we've demonstrated that it's a really capable vehicle and that there might be a lot of applications for it. So yeah. Let me see. All the way in the back. You mean to build or? Yeah, so we've spent, it's tens of thousands of dollars of materials. It's like 30 to 40, maybe 30K in materials. We've spent several tens of K on engines because we actually bought that expensive engine. So there's like, we probably have $30,000 in engine stuff. And that commercial autopilot that we didn't build in-house was about $20,000. So all told, there's about $100,000 in it. And then there's a bunch of labor and work and that kind of stuff. So, yes, sir.
I have a question about your astronaut selection.
Sure.
What was the interview process like? Was there, how many rounds? Was there a physical conditioning?
Yep. There's a paper application, and then there's a cut, and then there's 2 rounds of interviews with a cut in between. The interview process is awesome. We were joking. I was down there for a week. I was in Houston for a week interviewing in the 2nd round, and it's a bunch of stuff. I spent half a day with a psychologist, getting just asked so many questions. There's a lot of, like, I did VO2 max on a bike. There's an in-person interview. There's lots of team exercises. And I was joking with everybody down there, like, you should do it even if you know you're not going to make it, because it's so much fun to just go interview. So, yeah. Sorry, I can't. Okay, yeah.